Good morning, mathematicians. We're going to do try part 20 again. As yesterday kind of just turned into normal office hours and me being bad at algebra. Try part 20 again. Oh yeah. As yesterday kind of just turned into normal office. I guess I gotta figure out, I gotta go find that PDF that we were looking at. And actually, maybe I have a question for some of y'all that know some things in chat. Hello, Kostaka Corey, first in chat. Bad in algebra, that's impossible. Well, I found a way. I'm so talented, I managed to do the impossible. Okay. What was this document? I think it was by Sergio. So, I think we were trying to look at some spectral sequence stuff to compute some quaternion stuff. Right? What's good? What's good? It's all good. It's all good. Actually, Leo, maybe you know that. I don't know if you know this, but maybe Rod knows this. I don't know. I don't know if Rod's rolling up today, but we're back to the smallest O pluses, yeah. I was thinking about explicitly the Knuth formula, right? How does that work exactly? How does the explicit Knuth formula work? Like, say I have a 2 cocycle, right? A 2 cocycle of a Cartesian product of groups, right? Well, I have a function that represents. I have a function representing some cocycle. And so then, I mean, I should be able to decompose this, right? Like the, what am I saying here? Give me a second. As opposed to the non-explicit Knuth formula. Well, I feel like the Knuth formula isn't very, like, nothing I've looked at. I mean, I guess I just need to go and track through all the sequences to answer my question. But, like H2 should be something like this plus H1 GA tensor H1 HA HA plus H2 HA, right? It's something like this. And I was trying to think about, well, what is the sort of explicit mapping? Like, so there should be functions, let me call this psi, phi, mu, and lambda, right? So I should be able to take this function f that takes a pair G1, H1, and G2, H2. You think you know a good resource explaining it? Then please share. And now, like, yeah, I'm wondering, how am I supposed to decompose this function? Is it like my guess here would be that this is that you get phi G1 plus G2 and psi G1 G2. But then what the hell happens for this middle term? Like, mu of which of the g's? Do you multiply the g's together? Is it mu G1, G2 times lambda H1, H2? Like, that would make sense. Hello, Locke. Hello. You read the paper with the simple proof of Knuth formula and never saw it again. Yeah, every mathematician gets visited by the simple proof exactly once in their life. If you don't remember the proof, you're screwed. Exam's over now, so you watch Math Guy do math stuff while you hit your head against algebraic topology instead of being ready for tomorrow's class. Well, how else do you prepare for tomorrow's class other than hitting your head against algebraic topology? I thought that's just what you do for every class. More precisely, the quaternions is a group of order 8. Each of the subgroups are cyclic maximal subgroups. Right, we were looking at all this stuff yesterday. You linked it, but YouTube said no. Hang on, you know what, Leo? Let me give you ultimate power. Wait, how do I do this now? Oh, add as moderator, yeah. Well, it won't. Can review. How do I managing moderator? Yeah, let's do it. Let's see if that gives you powers. Let's see if that works. Where we use universal coefficient theorem. Right. Okay, we were just diving into some of these. You have no idea what these mean? Nice. It worked. Okay. Well, I will take a look at this later. It's spectral sequence time. Okay. So let's set up. We have... right. So we're already getting we know already that our E2 page is this. Right? This is the Lyndon, blah, blah, blah. Lyndon B. Johnson spectral sequence. Oh. Where was it? It was right there. Right. Right. So we have that E2PQ being HP, and now this is Q8 mod Q8 mod the, how do I make this damn message go away? There we go. Oh, there we go. Q8 mod the commutator subgroup, which was what again? I think, what did we get? The Klein 4 group? Was the commutator group the center in this case? Algebraic topology has been used multiple times to mix success. Oh, I missed a comment here. Algebraic topology is absolutely the right thing to do for your non-math classes. Yes, I agree. I agree. Yeah, neuroscience dude who's used it. That's interesting. I've heard of spectral graph theory being used in neuroscience. You're no longer a chatter of the people, you're bourgeois. Yeah, don't make me revoke your privileges, Leo. Nothing super crazy, but still impressive. Yeah, probably persistent homology. Oh, covering space theory. Huh. Interesting. Okay. Right, it was Q8 though. Q8 mod whatever our commutator group. We'll figure out what it is in a second. We'll remind ourselves in a second. And what do we have here? This was C2. That part was definitely C2. And then this is going to converge to this. Group cohomology coming next. Something you can maybe understand. Well, that's good. Bourgeois, indeed. Wow, Boris, you're gunning to get banned here now too. How could you possibly hate cover spaces? Such an incredible idea that leads to the étal version of all of this stuff. Okay, yeah, the commutator. Oh, the commutator is just C2. Okay, nice. So this should become Klein. Right, so this is C2. This should become Klein. And maybe I'll rewrite this as F2 just because it's our coefficients. Dan K theory. Oh, you tried and you failed. The proofs are ugly and not nice. Well, I don't know about that, Boris. I don't know about that. Same reason you hate matrices and linear algebra. Okay, you're making me upset. We are doing group cohomology. But there's algebraic topology mixed into that. Right. Okay, so... But what else can we say? So here, we're also using another fact, right? What is it? We're using the universal coefficient theorem to get the first isomorphism. Okay. Did we cover universal isomorphism theorem in this document? No, we did not. Oh, no, we did not. So, right, this is homework. We're reading somebody's homework right now. Universal coefficient theorem. I think you might be wrong this time, Leo. I don't think I'm a universal coefficient theorem. Jumping between very pure math and working computer science, you see linear algebra spoken of very differently. How could anyone hate the only thing we understand? Universal coefficient theorem establishes... Wait, are we doing homology or cohomology? What's going on here? I guess I can close that. Are we doing homology or cohomology? No, we're doing cohomology. I mean, whatever. There should be a version of both, but... Establishes relationship between homology groups with different coefficients. Right. The integral homology determines the homology for any abelian group. The usual proof of this result is a piece of pure homological algebra about chain complexes of free abelian groups. The form of the result is that coefficients over A may be used at the cost of using a Tor functor. For example, it is common to take A to be Z mod 2, so coefficients are mod 2. This becomes straightforward in the absence of two torsion in the homology. And do we... Okay, so we need to make some... We're going to need to make some Tor computations here then. Oh, this is spectral. This is a special case of the Bockstein spectral sequence. Oh, so we're gonna technically using a spectral sequence argument inside a spectral sequence argument. Homology is Tor. Oh, cohomology is X'd. It becomes X'd. I see. Oh, I see. And there's the article about it here. Off topic, but does anyone have a book recommendation for self-learning commutative algebra? Depends on where you're starting from. Yeah, I mean, Eisenbud is pretty good for, are you aiming towards, I mean, it's called commutative algebra with a view towards algebraic geometry. So if you're looking towards algebraic geometry, do that. But where are you starting from? Like, if you haven't seen modules before in any detail, then yeah, I would go start with a Luffy. Luffy's got tons of great stuff. Some people say don't and just start with algebraic geometry. I don't know if that's a good idea. I wouldn't say that. Although you could also just start with algebraic geometry, and backfill algebra as you go. I wouldn't suggest it, but I wouldn't warn against it necessarily. I might be a Tor computation. Actually, maybe I'm more of a next computation. I feel more cohomological in my heart. Did we spectral the spectral sequence? Not yet. Not yet. Okay. Wow. So we're gonna need to compute some X1s then, I guess, right? Wait, G module X1 into G? Where G is somehow a R module? Yeah, let G be a domain. What weird notation. G is I see. A module over PID. Okay. I guess maybe are those the computations we're getting into now? So for each one of these, we should get an isomorphism. Does the X die? Does the X just straight up die? Maybe it does. Maybe it does, right? Oh, and wait a second. So we've got lower indices, so there's homology going on here and cohomology. Okay, well, let me just write this out then, I guess. You feel like commutative algebra theorems fit into a narrative once you learn algebraic geometry? Yeah, I don't know. I feel like there's plenty of commutative algebra that makes sense on its own. Because of the existence of commutative algebra courses, a lot of algebraic geometry courses just skip the algebra proofs and cite them. Yeah. Okay, I guess let's do this. So, boom, we've got X1 of H I-1 of 1 I minus 1 of gosh, what are we, what's going to go where? So we're making a claim. Well, somehow we get a hang on a second. Somehow they're also getting this tensor product out. Oh, but that's probably fine. Maybe we're using a tensor Hama junction somewhere. Yeah, Dedekind domains as smooth curves is pretty cool. Let's go. You see a spectral sequence, do the sequence part. Well, we're not. I'm trying. We gotta build ourselves up to that, yo. Okay, so we're looking at something that looks like this. So what? I guess I'm gonna take my X will be V4, and my G is gonna be this thing. So I know that I have homology Klein group F2. So it's going to be X between that and this. And maybe I should call it, maybe I'll call this P minus 1. And that's going to go into, wow, I really don't have room here. So that will be just copying this here, V4, HQ, C2, F2. And that will go into HOM of HP V4 F2 into HP V4 HQ C2 F2. Man, this is nuts. Is this really the right way forward? You have a tough situation with getting these courses taught at your university. Yeah, that makes life tough. Yeah, talk to profs, always. You managed to make 0 progress on the Hatcher question. What was the Hatcher question? You wanted to finish, but you got distracted because you got distracted. Yeah, welcome to being a mathematician. I mean, we definitely have a sequence, not a spectral sequence, but we've definitely written down a sequence now. Okay, and now what? So I guess if we can show, I'm guessing that the isomorphism proceeds by maybe arguing here that X is trivial. And which I think it will be, because I think this ends up being yeah, I'm trying to think. The F2 cohomology of C2 is like always F2, and then that should be like I mean, yeah, as a vector space, everything's injective and projective, right? So that should be trivial. And then this thing in the middle, well, I'm not sure where we get the tensor product from, because I thought maybe once I wrote out this HOM, we would get a tensor HOM adjunction, but we've just got one HOM sitting here. So not so clear. But, okay, wait, some of the cohomologies in low degrees turned out to be HOM spaces. And there's something cyclic going on here. Yeah. I don't know. This should follow from the long exact sequence you get from derived functors? Huh? Pardon me? Oh, you're saying I should X into this short exact sequence? What are you saying? Yep, no problems with that. X1 is the first derived functor of Ham, sure. Universal coefficient theorem, okay. Okay. And so how did we get a tensor product? Oh, I mean, I get, is that what you mean by, no, they're just saying suppose it's this. Yeah, I don't know where this tensor product's supposed to be coming from. You're new to this. Well, welcome. Hello. To get the details, you would actually have to think, and you're morally against that. Fair. Yeah, fair. I mean, maybe we should just scroll through the rest. I don't know. We could take this on faith and then scroll through this person's homework and then go read an actual textbook. Switch over to an actual textbook soon. Yeah. Okay, so whatever. Let's just take this on faith. Let's just take this on faith and get to the actual spectral sequence. So we know that our E2 page is this. I guess we don't know what the differentials are really doing yet, but whatever. If we know our E2 page is that, then well, it seems like we're gonna have. I mean, X, Y, Z should all be like degree 1 stuff, right? So it seems like we have. I'm guessing we just multiplied degrees accordingly. So I'm guessing like, yeah, it seems like. Well, we'll have F2 here, E01, E11, E21. Well, maybe we can fill in. Maybe we can fill in some of this. Start filling in some of this stuff here. Wait, what am I writing? 0, 0, 1. This is 1, 1. Wait, what? Oh, this is 0, 2. What am I doing? 0, 2. 0, 2, and this is 2, 0, 3. This is 1, 2. Okay. Oh my god, I can't even index today. Well, hang on. We can actually compute some of these things, right? So we know what? I mean, this is what am I even thinking? Of course we can compute some of these things. Some of these things we know explicitly. I mean, I guess is this saying that every page is non-zero? Okay, let's see how the argument goes. Hatcher question you wanted to work on from start of stream was to show that the maps have some point X or minus X. Still working on braining it. I mean, that smells like some Brouwer fixed point theorem type stuff. So I mean, oh, you're still braining it. Okay, I won't give any hints or anything. I'll call you Pope based on the number of things you take on faith. You once said SU2 is isomorphic to S3 because, oh yeah, just look at it. It looks spherical. I mean, fair. Just stare at it hard enough, yeah. It's literally matrices. How did you see it? In your mind. In your mind. It looks kind of round. It just does, yeah. I agree. I agree. Yeah, it just does. Let's see. Oh, chat, I lost you. Where did I put you, chat? Where we used. Okay. We're gonna compute the image of D2. On one hand, that is that. So, wait. Excuse me. Why is that the infinity? Why is E2 1 0 infinity? Maybe if I draw myself a little grid here. Okay, let me go back to drawing myself a little grid. So F2 E 1 0 E 2 0 E 3 0 E 0 1 E 1 1 E 2 1 E 3 1 E 0 2 E 1 2 E 2 2 E 3 2. Do the isomorphism thing? Yeah. Back in a sec or not? Behave, chat. Leo's gone drunk with power. You forgot Halloween just happened. Did I do like a Halloween Spectral stream? I did not. Sorry, gang. Spectral sequence is all about drawing grids. That's true. Spooky spectral sequences. Okay, so what is the claim here? They're trying to compute. They're saying something about. They're yapping here about. So D2 goes from E201 to E220. Agreed. But they're saying that E201 is equal to the infinitieth term. E201. And where's 01? I see. Right. Because I guess it will never... Wait, how do they know that? How do they know that? Yeah, that is unclear to me. I mean, the killing form still is spooky. I would still say it's spooky. Yeah, I mean, this is unclear. Well, E10 then again is what the first. Ooh. E10 is the first cohomology of the Z2 coefficients of the quaternions, but we don't know anything about that yet. I mean, this seems circular. I don't know how we're saying that. Yeah. Maybe we shouldn't be reading this person's homework. Or Or maybe I'm just not getting something obvious. On the other hand, E2 here is equal to this thing is generated by degree 2 homogeneous polynomials in these variables. To find coefficients. Yeah, I'm not convinced by this is that this is non-zero, but I mean, the fact that it's non-zero could come out of this next step, because this next part does make this part of the argument make sense. To find coefficients, we use the restriction map on subgroups. We first consider the following map of group extensions and take the restriction here. It just looks circular, or does it look spherical? We define the restriction map here. Sure, I guess I could believe... Wait, what? A generator of this? What does that mean, though? Huh? Okay, I'm lost in the sauce. I think it's time to just go over to Weibel. That's what it is. You know what? You hate yourself. No, don't do that. You're going to pause the Hatcher question and start a representation theory book. No, don't. Don't. I mean, okay, wait a second. I mean, I'm very pro you starting a representation theory book, but don't finish the Hatcher question first. Let me then give you something of a hint, right? So think about the proof of like the Brouwer fixed point theorem, right? Where you have, what is it, like the Brouwer fixed point theorem on the disk, right? So how does that proof go? You take a map, or you do something. What is it? You look at something like, it's something like you look at like the inclusion. What am I writing? You look at like the inclusion of the sphere into the disk, right? And you also consider some map, some continuous map here, and you look at something like the composition of these two things, and that ends up inducing some map on homology, right? That ends up inducing some map on homology. It's like something like this. And then you make some argument there, basically. You can make some argument here about some fixed point theorem nonsense. So what I would do to solve your problem, because it seems, since it's in Hatcher and it seems a lot to me like this thing, I would recommend carefully looking at the proof. I think this proof is in Hatcher. Carefully looking at the proof and trying to mimic it. And I'm sure that that's the approach that will work. Why are you mad about inducing some map on homology, Leo? That's that's the dream. Isn't that what we always want to do? Induce maps on homology? Sniff it good, yeah. Yeah. There's other cool looking stuff here, but yeah, we should just go read an actual textbook. Oh, we do have this. Should I spend some time? I mean, my question about the Kunith, formula is relevant to spectral sequences. So, maybe we should be reading, maybe we should look at this document before going to Weibull. Universal coefficients and Kunith theorems. Yeah, I mean, this will be good for us anyways. So, either you're blind or the general fixed point theorem for dn wasn't in the section before. D2 was done before that, and you're sure? Yeah, go stare at the D2 one. Go stare at the D2 one. It's going to be some argument where you take this map on D2, you get an induced map on homology, you use something about retractions or blah, 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 and some proof by contradiction. And I'm confident that if you follow those same steps, it'll lead you to the same, to the solution. The exercise right before the one you're doing right now was to prove general fixed point theorem for dn, and you did that one. Yeah. So, okay. I try and copy those same steps. Like, yeah, see what you can say about induced maps on homology. Okay, in this chapter, we give proof of the universal coefficient theorem, which shows us how to relate these things with the tools developed to do so. We also prove the Kunith theorem. Okay. Suppose we have a chain complex of R modules, and what is S star X? Oh, I guess that's like the singular complex of a topological space or something. Universal coefficient theorem tells us concerns the failure of the natural map. Proof is in Rotman. Had the problem for homework. Well, learning, I don't think that's so crazy, Locke, I think sometimes it is good to learn about a powerful theorem and apply it first, Sometimes I think that is a valuable way to learn things. Learn how to use a tool, Most people learn how to drive a car before they truly understand how it works, right? I mean, some car nerds maybe are reading about cars before they can drive, sure, but I see. TMW, the moment when you split, but not naturally. Yeah. Yeah. So let's see. Okay, so this is a homological version, but whatever. Into Tor 1 Hn minus 1 tensor M. Okay. So, right. And the natural map comes from what? I got to turn off messages. Mind you, what's the point of turning off messages? I'm probably gonna end stream soon enough. Explain a junction to you? Well, you should go. You should go read. Go read Leinster's notes. That's what you should do. If it was normal office hours, I would explain a junction to you, but I'm trying to teach myself some spectral sequences. Why am I learning this? What's the motivation? Because it's cool and sick. I mean, spectral sequences are also not completely unrelated to my research. And actually, there is a more legitimate project I'm working on right now where, basically, I'm trying to understand certain group extensions with the Klein group, and I'm trying to prove some certain things. And it might be easier if I can decompose the functions, defining the extensions via the Knuth formula. I don't know. I do got a spectral sequence, yeah. There's also an analogy with the junctions from analysis. Actually, in my Who Gives a Sheaf series, I talk about, mind you, I don't think I motivate it very well. I prove a bunch of things about adjunctions in details, somewhere in like episode, 15 or something. And you don't need to have watched the episodes before because I sort of define adjunctions from scratch. But I really do it in in a different way than maybe it's usually presented, depending on how you first learn them. But you should go look at Leinster's notes. Right. Okay. So the map in question, though, we're thinking about the map from homology between these things. Right. So, right, if M itself was, well, okay. What is the point of the addendum? Usually you know the outer terms of a short exact sequence, and there's a number of possibilities for the middle. The addendum says that the middle term is always... Wait, the addendum? What addendum? The middle term is always a direct sum of the outer ones. Okay, let's just start wading into this. You don't know... You don't see why A cross B is optimal? Just call it universal? Well, not every limit is a product. Adjunctions give you some free limit colimits. Yeah, if your categories are total orders, yeah. But this comes up a lot of times. Like I was just, one of the students I tutor online. Hey, if you want to shell out some big bucks for some tutoring, let me know. But one of the students I was tutoring, we were going through the universal property satisfied by the abelianization of the group / the commutator subgroup, right? And like I think that's a good way to see limits and colimits as solving some sort of optimization problem, right? Because it basically tells you that the quotient by the commutator subgroup is the largest abelian quotient. So it's like the optimal abelian approximation to your group, right? That's what the universal property is telling you. Yeah. Okay, so we resolve M by free our modules. We can get away with a two-step resolution because it's a PID. Okay. And we'll use that for F free. Okay. Oh, and we use that if F is free, then this is an isomorphism. Sure. Tensoring the free resolution. We should get a short exact sequence. We get a short exact sequence of chain complexes. This uses that the isomorphism in that the assumption that each Cn is free. And this induces a long exact sequence here. Right. Exactness at the right terms. Exactness at the right terms? Are we just talking about the snake map going on? That moment when the optimal abelian approximation to your group is a trivial group. Yeah. I mean, yeah, it do be like that sometimes. You will report back in some future stream in case anyone remembers. Looking forward to it. Various category theory people tell you the point of categories is to define adjunctions. That's true. Well, is it true? No, I don't know if that's true. I gave a talk in a seminar recently. No, I won't even tell this story. You guess you don't get this. It's just the special adjoint functor theorem. Wait, what don't you get? Otherwise, not be exact. We obtain a long exact sequence on homology. Exactness at the right terms. Okay, so I think we're just talking about taking the snake map, right? Because we're going from the co-kernel here into here. Gives us a short exact sequence. Oh, sorry. Right. Exactness of this sequence at the right terms gives us a short exact sequence here. Sure. And then using that alpha is an isomorphism of R modules. We see that this is naturally isomorphic to this. Yeah, no problem, Matthias. Like you would say the point of groups is to define group actions. I would agree with you. I can just leave you on the story star. I can do whatever I want. You don't understand why the point of categories is to define adjunctions? I'm not sure if I would agree. I mean, the story I've been told, which makes sense to me, is that originally it was to try and capture the notion of natural transformations. I mean, adjunctions are awesome, and they're everywhere. Okay, I will tell you the story. I was giving a talk in a seminar on Lie groups, and I don't know. I mentioned the fact. That there's the adjunction between taking Lie algebras and taking the unique connected Lie group associated to simply connected, whatever. And I don't know, this guy, one of the people moderating it, was like, I don't know, he was freaking out about the statement. He was telling me, well, first he told me I was wrong because he thought I was talking about equivalence of categories. He was telling me that it's not adjunction. And then he said he didn't know what an adjunction was, but that he didn't care about it. And I was like, okay, but I'm that's fine for you, I guess. But I mean, hey, whatever. It's like partly this person's seminar, and they're like an established person and, you know, very talented and good and all that. And I guess they're more on the analysis side, so whatever. But I just found it very funny that this person is like, it's like, okay, it's like, yeah, I'm giving the talk and I'm telling you about this adjunction because I care about adjunctions. And then this person was, I don't know, upset about it, whatever. Not a category theory guy, I guess. Yeah. But the first term is just Tor 0, and the last term is just Tor n minus 1. Oh, yes, I see. True. Okay. By the addendum, we use that since R is a PID and each entry in here is free, then this is free. By lifting generators, we can define a splitting, which induces a splitting in the opposite direction. I see. Okay. I'm still not totally sure. Okay, I mean that's fine. I guess like this makes sense to me. This is fine. You would have done the exact same thing as that guy. Is abstract homotopy theory the gateway from analysis guy to category theory guy? Could be a gateway. Then if yes, you know how to convert one person, Oh, go and give it a try and let us know how it goes. Okay, maybe we'll come back to these notes tomorrow. It is about time that I get back to more pressing issues. I don't know. Looking at this, I don't have so much hope that this is going to help me make this very explicit, to be honest. And also, I guess I'm going to have to wade through this to do the cohomological version. Oh, yeah. Yeah, I don't know. I mean, whatever. I guess I should just be a big boy and compute the cohomological version myself, but whatever. Okay. Well, that is all for today. I will see you all tomorrow, and bye-bye. Nah, just kidding. I gotta